Hello, young chemists. Today we're going to take a little time to talk about Boyle's law, which is a gas law that shows the relationship between the pressure of a gas and the volume of a gas. So, Boyle's law says that as the pressure exerted on a gas increases, the volume of the gas decreases. Okay, so a gas is mostly empty space, so it's pretty easy to squeeze a gas into a smaller volume, right? So if you had a volume of gas and you squeezed it, it can force into a smaller volume. And we're going to do some calculations with Boyle's law, which shows this. So as the pressure exerted on the gas increases, the volume decreases. One goes up, the other goes down. We have starting conditions and ending conditions, starting pressure, starting volume, ending pressure, ending volume. The units here, it says pressure in atmosphere, volume in liters. It won't really matter what unit of pressure you have, as long as you have the same unit of pressure when you start and when you end. The same is true as volume. The mass will work out if it's in liters or milliliters. The math will work out if it's in liters or milliliters. So the first question says, if a bag of chips is packaged at sea level with a pressure of 1 atmosphere and a volume of 2.5 liters, what will the new volume of the gas be if the bag was taken to a convenience store in Crested Butte, Colorado, where the atmospheric pressure is 0.75 atmospheres? So the first thing we have to do is identify the variables. What do we know and what are we solving for? So the starting pressure is 1 atmosphere. Okay, so 1.0 atmosphere, that's our pressure at sea level. The starting volume is 2.5 liters. We don't know what the ending volume will be, but we do know that the ending pressure is 0.75 atmospheres. Okay, so we're solving for the ending volume. Next thing we have to do is plug those numbers into this equation. Okay, so P1 V1 equals P2 V2. So we have 1.0 ATM times 2.5 liters equals our pressure 2 is 0.75 ATM, and our ending volume is unknown. V2 is what we're solving for. So sorry about that. We're solving for V2. In order to solve for V2, as it says in step 3, it says isolate the desired variable by dividing both sides of the equation by the one variable given on the side of the unknown. So on the unknown, we have P2. So we are going to divide this whole side by the given variable on the side of the unknown. And if we do this, it will cancel, and you'll be left with V2 on one side of the equation. So I'll just write that down here. V2 is going to be equal to 1 atmosphere times 2.5 liters. Whatever we do to one side of the equation, we're going to do to the other. So because we divided by 0.75 over here, we're going to divide by 0.75 on the left side as well. And you can see that our units of atmospheres will cancel, and we'll be left with our answer, which will be a volume in liters. So if you take 1 times 2.5, that's 2.5, and that gets divided by 0.75, you get your solution, which is 3.3, that's repeating, and this is in liters. This is going to be what your V2 equals. Now, it's always good to stop and sort of look at your answer and think if it's about what it should be. So in this scenario, the pressure is decreasing, right? The pressure goes from 1 atmosphere to 0.75. So if the pressure is going down, that means our volume should go up. And if we start at 2.5 and we're ending at 3.3, our volume did go up. So it goes in the direction that we expect. Okay? So we're going to do a couple more examples. The next one is going to be solving for a different variable. So the next problem says a sample of carbon dioxide occupies a volume of 3.5 liters at 125 kPa pressure. So kPa is kilopascals. It's a unit of pressure. What pressure would the gas exert if the volume were decreased to 1.75 liters? So again, P1, V1, P2, V2. What do we know? What are we solving for? So it says that the sample of gas has a volume of 3.50 liters, and the pressure is 125 kPa. What pressure would the gas exert if the volume were decreased to, so we have an ending volume in this case, 1.75 liters. So we don't know P2. Now if we plug these into the equation, 125 kPa times 3.5 liters equals P2, which is what we're solving for, times 1.75 liters. So we need to get P2 all by itself on one side of the equal sign. So we're going to divide by what is on that side of the equal sign, 1.75 liters. That will cancel it out, leaving you with just P2 on the right side of the equal sign. Whatever we do to one side, we have to do to the other side. So 125 kPa times 3.5 liters is going to get divided by 1.75 liters. And liters will cancel, and you'll be left with your answer, which in this case is in kPa, kilopascals. So on our calculator here, we'll go 125 times 3.5, some number, divided by 1.75. Our units of liters cancel out, and we're left with 250 as our pressure. We'll include a decimal point at the end for 3 sig figs. This is our ending pressure. Now again, let's think about if this makes sense. In this scenario, our volume decreases. So we would expect our pressure to increase. Now, if you want to be more specific about it, look at how the volume changes. We go from 3.5 to 1.75. So that is actually half of the original volume. So if the volume is cut in half, look at our new pressure. It is 2 times what we started with. So this is inversely related, but inversely proportional. So if the volume is cut in half, the pressure doubles. Right? If the pressure doubles, the volume is cut in half. Next, we have a question where you are first given the pressure, and it then decreases. So in this problem, it says that the starting pressure is 1.5 atm. It says the pressure decreases to 0.5 atm, producing a new volume of, so we know the new volume is 750 milliliters. Oops, I wrote this in the wrong place, I'm sorry. 0.500 atm, that's our pressure. V1 says what was its original volume, right? Original volume means V1, so we don't know what the V1 is. Sorry about the scribble, that's what we're solving for. So to plug this in, we have 1.50 ATM times V1, which is what we don't know, equals 0.5 ATM times 750 milliliters. So just like the other problems, we need to get this variable all by itself. So we're going to divide by the thing that's on that side, 1.50 ATM. That will cancel and leave you with V1 on the left side of the equation. Whatever you do to one side, you're going to do to the other. So this gets divided by 1.50 ATM. When we do this math, the units of atmospheres will cancel, and we'll be left with our unit of volume, which in this case is going to be milliliters. So plugging this into the equation, we have 0.5 times 750 divided by 1.5. Our units of atmospheres cancel, and we get 250 milliliters, which is just sort of a coincidental thing that both of our last two answers were 250. One of them is in kPa and one of them is in milliliters. Again, ask yourself if it makes sense. Our pressure goes from 1.5 down to 0.5. So that means the pressure is 1/3 of what it originally was. And if the pressure decreases by a factor of 1/3, our volume going from 250 to 750, which is 3 times as great, makes sense, right? If the pressure decreases to 1/3 of the original, its volume increases to 3 times the original. Again, inversely related. Final question. It says, a sample of fluorine gas exerts a pressure of 950 torr. So torr is a unit of pressure with a volume of 250 milliliters. When the pressure changed to 2.5 atmospheres, what will be the new volume? So new volume is what they're asking for. That means they're solving for V2. So P1, V1, P2, V2. We don't know what the new volume is going to be. The starting pressure is 950 torr. Volume is 250 milliliters. And the ending pressure is 2.50 ATM. Now, it might be tempting to just plug these numbers into the equation, P1, V1 equals P2, V2, and start solving. But if you look at our units of pressure, torr and atmospheres, those are 2 different units of pressure. This is not going to work. So one of them needs to be converted into the other. So we can either convert torr into atmospheres, or we can convert atmospheres into torr. One has to be changed into the other. So how those 2 things are related, 1 atmosphere is 760 torr. That's our equivalent statement. So if I'm going to convert one to the other, it doesn't really matter which way you do it, but I'll just choose torr. Okay, so if I take 950 torr, to convert it, I say times something over something else. What I want to find goes on top, so ATM goes on top, and what I'm given, torr, goes on bottom. And we're going to use the numbers from the equivalent statement to set up our conversion factor. So 1 atmosphere over 760 torr. So if we take our number of torr divided by 760, okay, so here's our calculator here, 950 divided by 760, you get 1.25 ATM. Torr cancel. So now, instead of using this 950 torr, we're going to use 1.25 ATM. Now that that's in there, we can actually plug this into the equation. So 1.25 ATM times 250 milliliters equals 2.50 ATM V2. Excuse me. So we're solving for V2 in this case. We need to get V2 all by itself, so I divide by 2.50 ATM. That will cancel, leaving me with V2 on the right. Whatever we do to one side, we do to the other, so this gets divided by 2.50 ATM. Units of ATM will cancel, and we'll be left with our answer. Our volume in this case is going to be milliliters. So put this just right over here. 1.25 times 250 divided by 2.5 gives us our answer, which is 125 milliliters. Again, our pressure goes from 1.25 to 2.5, so that means our pressure doubles. So our volume should be split in half, and it goes from 250 to 125. Our answer makes sense. Hopefully this has been a helpful video. It's Boyle's Law. It's all about the relationship between the pressure of a gas and the volume of a gas. Keep up the hard work.